This video deals with Bohr's model of the atom. What are the problems? What are the strength point of Bohr models of the atom? Up to now, what we have seen is when we talked about the history of atom and the evolution and revolution that the structure of the atom have had. Remember, we start with Aristotle, which was saying there are four elements, and then we moved to Dalton, which was thinking and believing that the atom is an undivisible unit, and then J.J. Thomson model of the atom said that there are two parts on the atom, one that is positively charged and one that is negatively charged, and then Rutherford was the one that made it through the gold foil scattering experiment, brought the new model of the atom. And this model of the atom was very similar to the nucleus at the center, the same, it's known as the planetary model of the atom, nucleus at the center positively charged. And this is one of the reasons why Rutherford's planetary model of the atom is very important, because he divided those two charges, positive and negative charges, within the atom into two separate places. So now nucleus positively charges at the center, and the electrons are moving around the sun, around the nucleus, the same way as the sun, planets are moving around the sun. Okay. The nuclear model was a combination of gravitational idea and subatomic particles, but had several problems which we have discussed in when we did the EMR, or when we treated the EMR. And the main thing is that since we have a charge electron that is accelerating because it is moving into the circle that has a centripetal acceleration, should continuously radiate energy in the form of EMR. So therefore, the kinetic energy is being converted into radiant energy, and the electron should go to the nucleus, which is a thing that's something that doesn't happen in reality, because atom is a very, very stable structure of the matter. However, we know that Rutherford had a very good finding, and there are a lot of other things that we have used the Rutherford model of the atom in a lot of explanations of the experiments that are done. However, now was very well established that hydrogen is the most simplest and lightest element in the periodic table, and they were always attracted to the spectrum of the hydrogen. So the visible bright light spectrum formed by excited hydrogen gas consists in those four lines that are red, that is at a wavelength of, let's make it red at a wavelength of 656.21 nanometers. Green, that is at a wavelength of 486.07 nanometers. Blue, that is with a wavelength of 434.01 nanometers, and violet, which I don't have one, but just let's do blue, like black, at a wavelength of 410.12 nanometers. And then there was those four lines at exactly those four wavelengths. beginning of 19th centuries or the end of 18th centuries, a mathematician known as Balmer found an empirical formula that gives the wavelength of those four lines. And he was saying that this empirical formula, which you do not need to know, but is just for the purpose of explaining what is coming later, as constant 1 over 2 to the power of 2 minus 1 over n to the power of 2, where n is any integer greater than 2 and less than 7. So n can be 3, 4, 5, and 6. And RH is a constant, which is known as the Rydberg's constant, and it is 1.0972 times 10 to the power of 7. And the calculations that are done here is like if you have what is the wavelength for n equals 3, then you substitute it 1 over lambda as 1.0972 times 10 to the power of 7, 1 over 2 to the power of 2 minus 1 over 3 to the power of 2, and then you will find a wavelength of about 656.2 nanometers, which is the red spectrum. You don't need to know this. You don't need to calculate this. It is just so that you have, it's just so that you have an understanding of a background of why we are doing what we are doing. However, you are required to know that hydrogen has a spectrum that can be described with a simple mathematical relationship, and it is a discrete mathematical relationship. And then Bohr, receiving his PhD in the field of physics, started working under Rutherford in Manchester. And on the same year, Bohr would propose a model of the hydrogen atom that incorporated J.J. Thomson cathode ray tube experiment. So he was able to explain through this model the cathode ray tube findings. He was able to include the Rutherford's model, the explanation of the gold foil experiment. He was able to explain Planck's quantum theory, Rutherford photon theory, the emission and absorption spectrum for hydrogen, the equation, which is known as the Rydberg's equation for predicting the absorption spectrum of the hydrogen, as well as Franck's and Hertz's experimental results, which were for mercury atom, okay? In order to account for the existence of a stable electron orbit and a separate emission spectrum, Bohr made 3 assumptions, which are called postulates. A postulat is an assumed idea upon which the theory is based, and those cannot challenge you. You will have to accept them as they are. So the first postulate is that electrons move. Let's leave this. Electrons move in circular orbit, but they do not radiate energy. Orbits, and they do not radiate. So this is saying that as they are moving, they do not radiate energy, which kind of covers the fact why the electron is not losing continuously energy to and then colliding EMR and then colliding into the nucleus. So this stage, those orbits are known as the stationary states. Okay. The second postulate that that Bohr presented is that electron can jump from one stationary state to the other stationary state, but they cannot exist between them. So electrons jump from one state to the other, but not in between. They cannot stay in between stage. So then when the electron absorbs energy, it jumps up the energy level. When the electron releases energy, it jumps down in the energy level. And the difference between final and initial in absolute value will be either the absorption or the release of the photon that this is happening. Okay, and the third postulate that Bohr presented is saying that all possible orbits around the nucleus, only few of all possible orbits around the nucleus, only few are allowed. Each orbit has a characteristic of the energy and radius. So it can pretty much is saying that it cannot be into any radius or any energy level. But those energy level and those radius from the nucleus are unique to the element that we are, or compound that we are dealing with. So only, I will say this, only few orbits of electrons are allowed. They have unique characteristics, or they are allowed. Only few orbits. I will say unique characteristics of energy and radius. And they are following the equation that energy at the nth level is equal to the energy of the first level over n squared. And the radius at the n level, is n squared r1. So, and those are known as the n is as the principal quantum number for ground stage. N is equal 1 and n is part of integer. Actually whole number, not integer, because we have 1, 2, 3, only positive, not negative. So now for hydrogen, the first energy level for hydrogen, E1 is equal to negative 13.6 electron volts, and R1 is equal to 5.29 times 10 to the power of negative 11 meters. Bohr postulates were intended to work for all atoms, not just hydrogen, but it did not work out that way. For multi-electron atoms, the interaction between electrons require more sophisticated idea, which we will talk a bit more later on. It may be of interest to note that Bohr was not very good in writing down his idea. His PhD was delayed for many years because he had developed such a fear on writing, and finally he dictated his idea to his wife, who then wrote the thesis. Through all this life, he has had a very difficult time on writing, and when you read Albert Einstein paper, there was a very eloquent flow of words and ideas. When you try to read Bohr's papers, is like you'll get bored since on the first paragraph of it. Okay, here is a diagram of the energy level for hydrogen. Not the size of the energy level depends on where you are placing the zero. If you are placing the zero at the ionization level, then the ground state will be negative 13.6 electron volts. And you are placing the zero at the ground level, then the ionization will be at positive 13.6 electron volts. And just out of pay attention here, because this is a very important diagram to understand. In order to jump from one energy level to the other energy level, the atom has to absorb when it's jumping from the lowest to the highest, or emit when it is jumping from the highest to the lowest energy level. And the difference between the two has to be equal to, the difference of the energy level has to be equal to the difference of the two energy levels that you are going to. So let's work. So remember what we said, it's two are the ways that the electron in the atom are either going to the energy, moving to the higher energy level through the photon colliding or the electron colliding. Okay, remember that. So now, if the difference of the energy between the two energy levels is always final minus initial. Now we are dealing with two numbers that can result into a negative one. In order to express that as the absolute value, then we have always a positive number. So now we are dealing here with a light hitting the electron at a certain level, and then therefore the electron is jumping into a higher level, or when the electron is at a excited level, then it's going to the lower energy level, of then it is releasing a photon. So now this, based on the Planck's, is the H times F or HCO over lambda, depend what they are giving you, and that will be the absolute value of final minus energy initial. Okay, so now let's suppose that we have an electron that is dropping from the fourth level. So the electron example, the electron is dropping from the fourth level. So initial is equal to 4, and initial is equal to 4, and it is going to the second level. So n final is equal to 2. What is the energy And is it released or is it absorbed? So now, since we have the fourth, because this is ground level, and 1 and 2 and 3 and 4, the mechanics of it is that is dropping from the fourth, the electron is dropping from the fourth to the second. Okay, so this is final and this is initial. N2 is equal to final and N4 is initial. Now, in this case, what will happen with the electron is losing energy. Okay, it's going from negative 3.85 electron volts into negative 0.85 into negative 3.40 electron volts. Therefore, what will happen is that we'll release an energy in form of a photon. Okay, so now the energy that is dealing here, we are dealing here, is the release. So now the change of energy is the final minus initial. So this will be the absolute value of negative 3.4 electron volts minus negative 0.85 electron volts. Therefore, the change of energy is equal to 2.55 electron volts. And now, what is the frequency? Then this is release, because it is moving from a higher energy level into a lower energy level. What is the frequency and the wavelength of the emitted photon? So what is the frequency and the wavelength of the emitted photon? Then based on the fact that we are dealing with the exciting release, absorption or emission of a photon, then this will be H times F, or HC over lambda. To find the frequency, then we go the change of energy over H, so 2.55 electron volts over 4 because we know that it is in electron volts, 4.14 times 10 to the power of negative 15 electron volts times seconds, and this will be 6.16 times 10 to the power of 14 hertz. And when we are finding the wavelength, again using this relationship here, will be Hc over delta E. So 4.14 times 10 to the power of negative 15 times 3.0 times 10 to the power of 8 over 2.55 electron volts, and you will find that it is 487 nanometers, which actually corresponded to the green line in emission spectrum of Balmer's series. Okay, Bohr model has its own strength points and problems with it. So the strengths are that Bohr model is able to explain strengths was able to explain the size of hydrogen atom. The size of the hydrogen atom, the radius calculated. I will say H, but H2 just so. The Bohr model gave an ionization value. Gave ionization value of the energy. And we know now that that is the exact ionization value for the hydrogen atom. Bohr model could account for the formation of the spectrum line. So it's explain the formation of spectrum line in the hydrogen spectra. Because Balmer, Lehmann, Pashmian, and others used the mathematical relationship to calculate the wavelength, but Bohr's atom gave some results and a strong scientific base for the observed emission and absorption spectrum line. Okay, and we were able to explain through Bohr's model, we were able to explain some modification to account for larger nucleus. So we were able to explain large atoms, I will say. And most importantly, Bohr's atom used the nucleus idea of the Rutherford, even though that it used the Rutherford ideas, gave an explanation for the structure of the electron cloud. But there are problems on it. And Bohr's model worked only for hydrogen. Works only for hydrogen. And it requires a lot of accommodation for larger nucleus. It gave some, but not. It works perfectly for hydrogen. Bohr's model could not explain why the number of spectrum lines increase for some elements when they are placed in electric and magnetic field. So why numbers of a spectral line increase for some under the influence of magnetic and electric field, and was not able to explain the relative intensity of some of the spectrum line, why some are brighter and some are not. So not able to explain the relative intensity of spectral lines. Why some are darker, some are, and some are not as dark as the previous one. However, Bohr models was a success. His model is still used as a starting point for teaching the atom in the field of chemistry, and it is widely used in chemistry. This model will explain many of the known properties in group 1 and 2 especially, and then 13 to 18. Model breaks down the transition elements in the periodic table and has a lot of benefits on it. Next one will move to Compton's effect. Next video will be a Compton effect. So I will see you there.